How you can use your skills?
Basically, I'm a metallurgist and a welding engineer. And in EIL, I had to wear different hats, thanks to Mr. K. Tandon, as a corrosion engineer, quality assurance engineer, inspection engineer, and a certification engineer, and metallurgist and welding engineer, whatever, as the time demands. And that kind of opportunity we got in organizations in EIL, in both in the width and the depth that we are able to deal with in different fields, gave us some kind of gave us confidence. And I was a little lucky in the sense God was always with me, and my bosses were always with me. And with this, we were also given a little free hand to develop the specifications so that EIL will get a good name wherever we go, especially in the case of pipelines, where in the 1975, where I joined EIL, they're all following mostly Bechtel specifications. And we had an opportunity to have a look at, interact with a lot of international experts visiting EIL because it's an expanding, supposed to be a very promising economy. We didn't, Mohammed didn't go to mountain, but mountain came to Mohammed. Most of the international experts came to EIL, and that's how the EIL people who had sincerely dealt with the subjects really acquired sufficiently reasonably good knowledge so that they can develop specifications. And as our philosophy go, anything that we do should bring laurels to the company. It means whatever we do, which should stand the test of time and should stand without any problem throughout their life cycle, lifestyle, whatever, design life and beyond. Most of the things. And especially in pipelines, we always expect to be beyond, as our inaugural speaker was telling. And what is required is you find out all the possible problems that can occur in a pipeline's life cycle, and then try to plug it at the beginning itself. Any activity that is well begun is supposed to be half done. That's a saying, as the saying goes. So we always try to do this department headed by him at that time. We had always strived to do the things well in the first time so that the problems will not occur. The main problem, especially in public sector, is when you solve the problems well ahead of time, you are not much recognized. See, all of us have got heart. How many of us really think about the heart till at the age of 45 or 46 when it starts giving some problems? Then only we know there's something like heart. Oh, it's very important. So likewise, when the problems start occurring, only then, so the emphasis most of the time was, you don't solve the problem at the right at the beginning. Try to keep something and for which you have the solution, and when the problem comes up, you give the solution and you become a big shot. Then you get promotions, you get whatever laurels. This is the concept that's prevailing and is one of the constraints that we face in most of the organizations, both private and public sector. And this was not encouraged in the EIL. We always wanted to do the specifications right. We say, for the integrity of the pipelines, let's now concentrate only on the pipeline issue. The pipeline's integrity has got, I think a lot of speakers yesterday has really covered it. What are the steps? It is the integrity, at the start of the thing, specifications, so that unless you you really want to know what you want to get, and then you know how to get, and then how you specify all those steps that will ensure that you get what you want. And then after you have got it and established, you see to it that subsequent operations also knows what is required, what are the limits within which all these parameters, the safety or integrity will be maintained. And all these steps are are the essential steps for assuring integrity. As he said, half well begun is half done. The beginning of any project conceptualization is the specifications. First, the specifications, if you want to build a house, what if you think, plan well everything, and you exactly know what you want, and you know if you are informed about the specifications based on the other's experience, that it will come for how long it will survive, how long it will retain its shine, etc. Then you get those materials from the known sources, and you inspect it properly, and then apply it properly. Then you are sure that your house is going to survive for as long as time as possible with minimum maintenance. Of course, maintenance is there. Therefore, the same thing, the integrity of the house can be extended to integrity of any projects, and so is for pipeline projects. The pipeline projects have got 2 or 3 essential things, like the most we find. Mr. Suri has not come, otherwise we would have known about the stainless steels. See, the metallic materials, of course, pipelines can be made of metallic materials, solid metallic materials, clad metallic materials, or non-metallics, such as any one of those polypropylene, polyethylene. It's not a coating, it's a solid itself, and fiber, FRP, those kind of things. So even there are pipelines with Teflon, because of course small diameter, where the corrosivity is very high. The materials that you choose, all of them have to be constructed out of materials. Now, out of these materials, steels are the most favored one, because it's quite inexpensive, and we believe that we have understood much about it. In fact, we have not. Quite often it fails where we believe that we know everything, and it has got a very good strength, and as long as you take certain precautions, it retains its properties throughout with time. I mean, it doesn't deteriorate that much, provided you take certain precautions. Your material that is you do a testing at 1960. If no corrosion or no deterioration you have permitted, then in 2015 you test, it will have the same properties. But they also have difficulties in the sense, because of this steel and its variations, like it could be a low alloy steels, or it could be a low carbon steels, micro alloy steels, online accelerated cooled thermomechanically, all variations are there. Steels are the very reliable and materials of construction. Therefore, what is required to be, but unfortunately they are also prone to deterioration by corrosion when things are favorable, and they are prone to deterioration by mechanical damage when digging, etc. Only these 2 things can create problem. One is mechanical damage, either by vibration or by other impact damages by an extraneous action, or a corrosion. So the specific material specification meant for integrity will have to be chosen very carefully, so that it has sufficient strength for the kind of application that we want. It has sufficient corrosion resistance for the application we have chosen, for the service medium that we are handling, and it is capable of receiving all the protective measures that we take in order to extend its life. See, these 3 are the crux of materials. And second is, it's not sufficient if you really choose the material. It has to be made into the form of your choice, so that it can be an engineering component. Therefore, the material that you chose should be capable of retaining all its chosen properties in all the operations that you do subsequently, like metallurgical operations, such as you are casting, you are rolling into plates, and you are going to bend, you are going to weld, and subsequently you are going to do some kind of heat treatments or hot bending, whatever operations that you cause. And you are going to coat. The coating also involves certain amount of temperatures, and it should retain its properties till that particular point of time, till you commission. And subsequently, when you do the therefore, and as the length of the pipeline increases and the pressure increases for handling, because for economic reasons, then we have to deal with the larger thicknesses. in the classical materials such as API file, etc. Naturally, you would like to, every company would like to decrease the wall thickness so that, which decreases the total quantity or weight of the material that is being bought, and hence you want to go for higher and higher strength materials. Retaining all the properties, the reliability and property of the steel, you should have a higher strength so that the wall thickness can come down. When you do that, then what are the issues? What are the elements that will go into it? What are the deleterious elements that will affect its long-term performance? So those knowledge of that basic metallurgical knowledge has to be incorporated into the basic material specification so that it retains its properties during the plate rolling process, during the pipe making process, during the field welding process, and during subsequent hot operations, whatever, including the field coating steps. Therefore, this is where our smartness lies, and not only that, as the thickness decreases, there are issues related to, you see, nobody wants to give more corrosion elements than absolutely required for pipelines, because that's again going to increase the wall thickness. And because of that, we try to incorporate certain elements such as copper into the system, so that the atmospheric corrosion resistance or atmospheric weathering can be well contained till it is really commissioned. Both internal as well as external surfaces can get oxidized, can get rusted, and that much a rusting can result in about 0.3 millimeter metal loss in about 3 or 4 months if it is left uncared for. So we try to incorporate certain elements in a small quantity so that its atmospheric corrosion resistance is increased. The main component is some amount of copper and some amount of chromium, nickel, etc. But again, there are limits. And now we are talking about you can't change the corrosion resistance properties too much. If the corrosion resistance, if the material, this pipeline cannot be handled with a maximum corrosion allowance of 3 in its lifetime, when it's going to exceed, you have to go for a better material or a surface protection which gives a barrier to the environment as being handled. The other one is, then when a carbon steel is a choice because of the cost, you can't go for higher metallurgy, then you will have to have an incorporate appropriate inhibition schemes. The inhibition scheme, how it's going to react with this material, whether it is the material is capable of handling the inhibition program, and what are the limits, what are the dosages, what is the frequency, what is its consequences, and if the corrosion can be permitted 3 millimeter, what is the corrosion products is tolerated in the pipeline itself or outside downstream units. So all these things go into the making of the specifications. See, once the specification is made, the specifier should also see to it that during the pipe making processes, whether it is capable of giving the accurate dimensions. See, another part of the specification is the dimensions of the pipe itself. Now, you may be wondering how it is affecting the integrity of the pipeline. See, if you have, while doing a field welding or the shop welding itself, there is something called, when you do that, naturally every strength, it is in the elastic limit, and there can be spring back. Even after, therefore, you have to specify in order to avoid the spring back so that the high-low will not be there, so that the root of the pipe is also very, very smooth, so that any stress rises caused by the high-low at the joint of the pipeline, either the long seam or the spiral seam or the circumferential field welding process. There will be the change in the surface morphology at that location, and that will be the sources of stress rising as well as preferential corrosion. And some of the corrosion products can get accumulated at that location, and underneath that deposit there could be internal corrosion can occur. And because of that, we give a specification which limits these, and the specification also should be capable of understanding whether it is possible to achieve these limits at the fabrication shop. Fabrication shop could be a mill which is making the pipe, or it could be field. And see, there are some inherent tolerances permitted by the specification over any dimension. If the diameter means it can be plus minus. If it is a high-low, there's a range. It's not an absolute 0 or absolute 2. So then you have to give a specification in such a way that it is aligned in such a way so that it comes within the maximum permitted. And the second, the route has to be as smooth as possible, so that the transition, if it is there, it's not sudden, it becomes smooth. Therefore, the welding of the route that you take, the specification, you have to create a subsequent fabrication related specifications, which talks about the quality, the various welding parameters that you should assign. You should decide the process, welding process that will give you the best kind of mechanical properties as well as the route finish properties. The mechanical properties includes the toughness of, depending on, for many applications, the toughness, even though it is not a low temperature application, the toughness is a criteria because that gives you the better tolerance for an existing crack to propagate. So it prevents an existing crack under the stress conditions to prevention to propagate. It prevents it from propagating further. So the toughness, in many cases, it's especially in gas lines, toughness is a criteria. So the material, again, the material specification to take care of the material composition, the microstructure, your heat treatments that you give to them, and should be capable of yielding this kind of toughness values. And secondly, any material, as the thickness increases and the strength increases, now many of the fabrication codes would require you have to do the heat treatment in order to recover the properties, especially at the heat affected zone. Because you are changing the history, thermal history of the material, that thermal history has been stitched to achieve certain properties, mechanical properties. When you change the thermal history by a welding process, then there is a sudden cooling from the material is heated above the so-called critical temperature, AC3 temperature, and cooled by a heat sink effect of the neighboring large amount of material. So that is going to make it, the microstructural changes, hardness changes, all these things can occur. Therefore, when that occurs, then the material should be capable of handling it. The normal conditions, and for other piping, we will go for a post-well stress heat treatment. That is not possible. If you want to retain the integrity throughout its life, the heat affected zone properties have to be retained, to be recovered to the original specification. Therefore, when in the case of pipeline, there is no heat treatment is not possible because it's impossible to do the heat treatment. Because of that, the material specification is itself stitched in such a way that in the as welded condition, it will be capable of yielding all the results, minimum results that we require. How it is done? The main criteria for the heat affected zone property deterioration is the carbon and carbon equivalent, because it increases the hardness and the hardenability also. So you limit the carbon content, you limit all the elements that are contributing to the or appearing in the carbon equivalent formula like chromium, molybdenum, silicon, etc., to a level where you are able to get the strength. At the same time, you do not get into a problem region in the heat affected zone without heat treatment. For all these things led to the development of a series of microalloyed steels where the carbon content could be very low, extremely 0.03, 0.08 and less. Normally it is in the vicinity of 0.05% carbon, and the chromium is restricted, molybdenum is restricted, manganese is also restricted because, again, the reasons I will tell you later. Then when it comes to handling a sour service applications where the integrity, most of the integrity studies started only after the introduction of the sour service pipelines. Because that's where the problems was recognized, and it was extended to various other things. And the earlier pipelines were not capable of handling these sour services. But when per force you have to go for either H2S is going inside or it's broken through for various process upsets, etc. So when it comes to server service, then there are additional restrictions ought to be placed on the specifications for maintaining its integrity throughout its life. What are they? Any server service, yesterday we saw stress corrosion cracking. When a H2S is present, it becomes slightly, the pH is depressed, because when the moisture is also present, in the absence of moisture, there will not be a problem. Either the crude or a gas, with the moisture and the service present, it is classified as a server service for certain partial pressures. When when it occurs, 4 kind of material deterioration will occur. So what he said, material specification should take care of anticipate all the material deterioration mechanisms that are possible during the lifetime of the pipeline, of the project on this pipeline project, and then anticipate it and solve it. So this was well studied by NACE, and NACE TM 0177 was 75 was a specification which was developed, which was subsequently EAL contributed much to modify that, and we are using a much tighter specification which was adopted by NACE subsequently in 2001. So there, the H2S can create problems like hydrogen-induced cracking, because it reacts with the surface to create nascent hydrogen that goes into this material in the long run, and wherever inclusions are there, it will get accumulated there and create a separation. It's called there is hydrogen-induced cracking. It doesn't require a stress. Then hydrogen-induced stress-oriented hydrogen-induced cracking, SOHIC. This same phenomena, but it occurs where the stress is also present. Especially stress is present because of the welding. Welding creates a lot of stresses at the weld joint, because there is a shrinking of the liquid metal, and the shrinkage stresses are not accommodated by movement of the neighboring material, which is cold. So because of that, the residual stresses are kept. Under that stress conditions, stress-oriented hydrogen-induced cracking can occur. The third problem is sulfide stress corrosion cracking. We said sulfidic yesterday was telling, because we call it sulfide stress corrosion cracking, SSCC. Then the third is, if there is a carbon dioxide related, CO2 related stress corrosion cracking can occur because of the external protective coating we are giving, like example coal tar enamel, etc. It can give rise to, the carbonates are available either inside or outside. They can also give rise to stress corrosion cracking. So they then call blistering. There is another phenomenon of blistering, where the hydrogen that occurs gets accumulated very close to the surface underneath, and then when hydrogen atoms enter, it enters an atom. It doesn't have a volume. When 2 atoms join together, it becomes a molecule, and then becomes a gas. Now it has got a volume. When it's not possible to accommodate it, and it produces a lot of pressure. When such a lot more hydrogen H2 gets accumulated, and it just tries to expand. If the ligament is very thin, it forms a blister. It forms blisters. All the 4 phenomena are possible, and it's called soft zone cracking. It's very close to the heat affected zone. There is a small region which has lost its strength. The hardness is also less, strength is also less, and there also it creates cracking. All these 5 phenomena has to be tackled while making the specification for assuring integrity of a service pipeline. It is taken, the method by which through the specification how we control is, the carbon equivalent is controlled, the chromium and molybdenum is controlled, the manganese is controlled. I said carbon to be less than 0.05, I was telling. Basically it's less than 0.08. It can be variation. And the inclusion content, see, most of the HEC occurs when the hardness is less than RC22, sulfate stress corrosion cracking is taken care of. When the inclusions are limited or eliminated, the HEC is controlled. Then when the HEC, how do you remove the inclusions? Well, when the inclusions are formed, the non-metallic inclusions are formed while casting, and subsequently it gets rolled. While it's getting rolled, it becomes elongated inclusions. And the elongated inclusions at the extremities, they are all stress races. So in order to avoid that, we decrease the sulfur level, because most of the, what is creating problem is manganese sulfide. So limit the sulfur to less than 0.003. Then, since manganese sulfide is found, manganese is also limited to maximum of 1.6, even though it is wanted for giving the strength, that also has to be limited. And if any manganese sulfide is also formed, that will be, the shape of it should not be in the elongated form, it has to be in the rounded globular form. To ensure that, we add some amount of calcium, so that the calcium, when the oxygen is present in the steel, calcium oxide will be formed first, and around that calcium sulfide will form. So calcium oxide, calcium sulfide, the globules are stable, it doesn't get rolled into a elongated inclusion in the case of when you do the rolling. So these are the steps we take. All these tests are to be incorporated in this basic specification. Okay. Okay. This kind of the precautions are taken. How I'm telling this topic is how materials and fabrication is important and ensuring the integrity. The subsequent, the fabrication aspect of it. The fabrication, I said, fabrication involves the rolling, bending, and it involves welding. The welding, any classical welding, any shielded processes, this flux shielded processes introduce hydrogen, because there is an inherent hydrogen in it, because there is amount of binders are there. Like you use a field welding. In the case of factory welding, the heat input is so high that even if something enters, because of the high heat input, it has sufficient time to move out. And submerged arc welding process, or gas metal arc welding process, or GTAW process, gas tungsten arc welding process, which has no hydrogen introduction at all. All these things have to be specified to start with. In the case of field welding process, classical method is to use for shielded metal arc welding with a cellulosic electrode, 6010, 7010, like that. So, because the pipeline has to be the pipeline project has to move very fast. The pipe laying speed decides the pipe welding speed, especially the root welding speed, decides the pipe laying speed. So when the schedules are shrunk, you want to do it as fast as possible. Naturally, then obvious choice is to go for 6010 electrode. That's a cellulosic electrode, which is for the root as well as the rest of the process in a vertical down position of progression. This ensures this has got a very deep penetration. So the root, because root has to be well fused, there should be no defect. So root fusion is ensured by the penetration characteristics of the 6010, it's fine. And subsequently they use either a non-cellulosic electrode in a vertical opposition with a higher deposition rates, or you can use cellulosic electrode itself. But as the strength increases, the cellulosic electrodes cannot be used, because the hydrogen related problem, hydrogen induced, it's called delayed cracking problem, can occur when you use for high strength steels, you introduce hydrogen by the process of using cellulosic electrodes. So under those conditions, then the material specification, the fabrication specification on field welding specification has to lay down certain conditions, such as the root has to be done either if the root is a large diameter, if it is approachable, you go inside, grind it and re-weld it by a suitable process with a hydrogen-free process like a GTAW, or if most of the pipelines are done from outside only, the root will have to be welded with a gas-shielded process which doesn't introduce hydrogen, such as gas tungsten arc welding or gas metal arc welding process. And subsequently, you can introduce other low hydrogen processes, or flux cored arc welding process, or for field welding. Or it can be a flux gas metal arc welding process. So you have to specify this. When in the case of and then the high-low that you are preparing, especially for X80, if you want for high strength grades X80, the perfect root match is a very essential requirement, and there should be zero tolerance, zero root high-low at the 6 o'clock position and 12 o'clock position. Other positions it is tolerated. So you have to, unless you specify that, they won't be able to manipulate to create this. Or you have to do a edge preparation at the site. The edge preparation tools are available, which is done at the site itself. you have to employ that. That also you have to specify in order to get the assured quality. Once the welding is perfect and subsequent the specification also, the basic specification also specifies what kind of coating you have to give. You have to specify the coating, its curing parameters, and its thickness, and its inspection requirements. All these things are controlled at the start of the project, which means you are bound to succeed if you do the things very well if you do not, see, once no quality can be inspected into a product. The quality assurance system should incorporate all the necessary steps right from beginning to the completion and hand it over. And subsequent quality assurance system can take care of the operation. We are talking about the operation discipline yesterday. The operation discipline also, the basic specification, process as well as material specification should also specify what are the limits of to what pressures variation it is tolerable, to what variation of moisture content in the fluid, handled fluid it is tolerated, and what are the poisons that it should not come. All those limits are to be prepared and passed on to the operator so that it will be appropriate monitoring can be approved. So the crux of the matter is the material specification, the starting specification, material specification, fabrication specification, the coating specification, and the inspection specification. So you should also you have to specify the appropriate inspection tools and procedures which can detect all possible defects that are likely to be occurring in the process that is chosen for the fabrication, and which are likely to create problem later. So you should, the sizes, the lowest sizes which can grow later, that lowest size it should be capable of detecting with predictable accuracy and probability of detection. So each one of these topics specification can be talked about for 3-4 hours. A lot of material is available in the public domain, but it's enough if we appreciate now, yes, the specifications are the root cause of many of the problems. And if the specification is perfect, and you can concentrate all your efforts for controlling the integrity on the subsequent steps, so that you get more time, you can divert more money and more attention to that. Thanks.